Welcome to this lecture on Earth's geology and climate for AP Environmental Science. This PowerPoint is going to wrap together some of the concepts that we've talked about in previous videos regarding Earth's tectonic activity, as well as some of the climatic variables. For the topics, we're talking about topic 4.8, Earth's geography and climate, and we are still with this enduring understanding of Earth's atmospheric processes are driven by input from the sun. All right, so pretty much all of the atmospheric processes are driven by solar input. Tectonic processes, which we will touch on today as well, however, are driven by energy from the core of the Earth or from the formation of the Earth and all of the radioactive materials that are still in the Earth's core and mantle. The learning objective, describe how Earth's geography affects weather and climate. That's where we're going to stick with most of today. Part of that includes topic 7.3, which is thermal inversions. So we will also talk about what a thermal inversion is and how they are formed. As usual, I've listed the vocab so that you can pause this and write this down now. And we'll start with this slide, which is literally copied and pasted from a previous PowerPoint, the PowerPoint on tectonic activity. So remember that the Earth's crust has not been static, that the continents do move. They move at about the rate that your fingernails grow. Some plates move a little bit faster than others. It is a very slow process, but it's significant over geologic time. So we're not talking about human timescales, we're talking about geologic timescales. Thousands, tens of thousands, hundreds of thousands, millions, tens, hundreds of millions of years. Okay. Plus, in addition to these, there is the intensity of the solar radiation, which does fluctuate a little bit. Not enough to really do too much in terms of climatic changes, but a little bit, especially if it lines up with the Milankovitch cycles. The tilt of the Earth is responsible for our seasons. Right now, it is at a 23.5 degree tilt relative to its rotation around the Earth, its plane of rotation. We'll talk about the Milankovitch cycles in class, so you don't have to worry about those right now or here. And then this is where we're focusing on today, geography, how geography is going to affect climate. So how does geography affect climate? Well, it does it in a number of ways. Ocean currents, geography is fundamental in the shaping of, not only just the continental land masses, but the ocean that is, or the oceans that are surrounding those land masses, and then the currents that are in those oceans. Whether there's land at the poles or not, whether the continents are all together in a supercontinent or if they are all in smaller continents, rain shadows, volcanic eruptions, and some other factors that we might touch on, but that we won't really focus on too much. We'll watch these videos in class, so I'll just skip this for right now. So like I said, the position of the continents is going to determine the shapes of the oceans. It's going to determine which oceans are connected and which oceans are isolated, and the currents that flow around these oceans or through these oceans. Okay, and those currents are going to move warm and cold waters all around the world and make sure that the poles are not as cold as they could be, and that the tropics are not as hot as they could be without those currents. Okay, cold water from the poles is moving down towards the tropics. Warm water from the tropics is moving up towards the poles in general. All right. And I should point out that water has a very high heat capacity. You guys should remember what heat capacity is from biology or chemistry, but essentially heat capacity is the amount of energy required to heat 1 gram of any substance by 1 degree Celsius. Okay, some materials heat very easily and they don't need a lot of energy to heat. Water actually needs a lot of energy before it heats up even just a little bit. Think about boiling a pot of water on the stove. It takes quite a while for that pot of water to boil because you have to put a lot of energy in it to raise its temperature. Okay, as opposed to something like iron, which is going to heat up very, very quickly. It's also going to lose heat very, very quickly. So water is going to be able to carry its heat from the tropics up to the polar regions, or at least the higher latitudes. Okay, and that is going to help moderate climate in those areas where you have these warm currents flowing. Where you have warm currents flowing, you have warm waters around those land masses, and that's going to heat up those land masses a little bit, keep them a little bit warmer. And the example that I have here is Northern Europe or Northwestern Europe versus the same latitudes in the Americas. This Gulf Stream current is bringing warm waters from the Gulf of Mexico, the Caribbean, up to Northwest Europe and Western Northern Europe, most of Europe. And it's heating Europe. That's the reason that at the same latitude, Germany is not nearly as cold as Labrador and Canada, or Spain is not nearly as cold as New York City, or the British Isles not nearly as cold as Ontario. Okay, so those warm waters from the Caribbean are traveling up to the European continent and heating up that continent. All right. On the flip side, cold currents are going to cool land masses. And the example that I have right here is the California current. The California current comes down from Alaska down the coast of the west coast of the United States. There is this warm current, this North Pacific current that goes up in here, cools. It's actually a little bit more like down here, cools, and forms this California current. All right, but in general, if you are on the west coast, a beach at the same latitude on the west coast is going to be much colder than the same beach on the east coast. All right, especially if you're at a more lower latitude. All right, so a beach in North Carolina is going to be much warmer than in the same latitude beach in California. New York City is going to be warmer than Portland, Oregon. All right, it does have a little bit of a flip side when you're talking about like right here along the Pacific Northwest and all of the islands of the Inland Strait, where this warm current, this North Pacific current, is warming them. But that's very similar to the Gulf Stream over here warming Europe. All right, but in general, this cold California current in blue is cooling the beaches on the west coast, which is why they are much cooler than the same latitude beaches on the east coast. All right. But I should point out that wherever you are on the planet, whether you're talking about a warm or a cool current, the ocean, this large body of water, is going to moderate the climate in any coastal area. All right, coastal areas are not going to be as hot as the rest of the interior land. Think about, look up here towards Morocco. All right, there's also mountains there, so that helps. And it's also not going to be as cold as interior areas are as well. So wherever you have oceans, they're going to moderate the temperature just because it's going to take a lot of energy to heat up that water, and that water is going to lose its energy over a long period of time, and it's going to moderate the temperature wherever you are. All right, but the cold and warm currents are definitely going to influence local climate. There's some currents that can have a global impact, and there's some geographic features that can have a global impact in terms of currents. The example that I have here is the Isthmus of Panama. When the Isthmus of Panama was formed, it started forming about 20 million years ago. It fully closed about 3 million years ago. If you know your geologic history, you'll know that 3 million years ago is about the same time that the ice ages started. All right. It's believed that by cutting off the Pacific and the Atlantic from one another at these mid-latitude regions, that it altered ocean currents so much that temperatures weren't more effectively distributed all around the globe, and that the poles got colder and the tropics got a little bit warmer. And as the poles got colder, Antarctica was also migrating to the South Pole, and it resulted in this drop of global temperatures. We'll talk about the significance of Antarctica on one of the next slides, but it resulted in drops of global temperatures, leading to those ice ages. But I should also point out that the ice ages are heavily influenced by the Milankovitch cycles, which we'll talk about in class. But anyway, the land at the poles, especially the example that we have today, Antarctica, and not quite at the poles, but Greenland. When most of the land is in the tropics, glaciers can't really form in the tropics except for at very high latitudes. All right, so in the tropics, if most of the land is in the tropics, you're not going to have a lot of ice formation on the planet. But when you do have large land masses at the poles, you are going to have a lot of potential land for ice to form if conditions are right for ice to form there. Once ice starts to form, you start to have a positive feedback cycle where the ice is going to further cool the planet due to its albedo effect, which we'll talk about on another day, but it's essentially just the reflectivity of that surface. Ice reflects a lot of solar energy back up into space and therefore cools the planet because that solar energy is not down here at the surface or in the atmosphere. But ice is going to reflect solar radiation back into space. It's going to cool that area, leading to more ice formation, which is going to have more surface to reflect back into space the solar radiation, which is going to further cool that area, which is going to lead to more ice formation, etc. So when you have this land at the poles, it starts this positive feedback loop if global temperatures are right for more ice to accumulate and form. As more ice forms, that's going to that's going to drop sea level because that water is locked up in ice rather than being in the oceans. And it's going to reveal land masses and allow animals to migrate across different land masses, and it's going to affect the climate of those land masses. Sticking with land masses, large land masses can regulate climate or can influence climate, and the center of those land masses, because the center of those land masses is typically deserts. The reason for that is most of your water is evaporating from the oceans. As it evaporates from the ocean, some of it just precipitates over the ocean and just rains back into the ocean and it's back where it came from. But some of those clouds will move over land. So the wind will blow the clouds in the prevailing direction and move those clouds over land where they will precipitate out. Now let's look at Europe. The prevailing wind direction is a westerly, so it's coming from the west towards the east, blowing all of these clouds over the British Isles. I guess I'll do blue. Over the British Isles where it will rain. It will rain over France. It will rain over Germany. It will rain over all of Europe. But as those clouds drop all their moisture, they diminish and they get smaller and smaller, and there's no oceans to feed them as they continue to move west. And those clouds have dropped all their rain in Europe, and by the time they get to Central Asia, there is no rain to drop anymore. So it leads to a giant desert in the middle of Central Asia. All right, we've talked about, or at least a series of deserts. We've also talked about the Hadley cells, and Hadley cells will definitely affect desert distribution as well. Remember that 30 degrees north and 30 degrees south is where your Hadley cells are. So even though there is, the Arabian and the Sahara deserts surrounded by ocean, they are still they're still very, very dry because of the Hadley cells. Plus, your prevailing wind directions is more like this, moving that warm, moist air away from those oceans, or sorry, those deserts. The next thing that influences local climate are rain shadows, and this is due to mountain ranges. So where you have a mountain range and you have prevailing wind direction, you are going to end up with a rain shadow. Okay, so say that there's an ocean over here. That ocean allows a lot of evaporation. You have all of this cloud formation on the west side, in this case, on this diagram, what I am going to call the windward side. So this is the windward side. The clouds blow over towards the mountains, and then they kind of get squeezed, right? They can't go up here into the stratosphere. They have to, that's obviously an exaggeration, not drawn to scale, but they can't go up into the stratosphere. They get squeezed down. They get cooled by the cooling effect of these mountains, and they drop all of their moisture on the windward side of the mountain, which leads to still wind coming, but no more moisture. So cool, dry air descending, which is going to lead to a desert on the leeward side of the mountains. So the windward side is going to be very moist, typically forest. The the leeward side is going to be desert. Okay, you see that happening in these two examples that we have down here. This is the Amazon rainforest. The prevailing wind direction is this direction, an easterly from the east to the west. It hits the Andes Mountains, drops all of its rain on the Amazon side, on the east side of those mountain ranges, and you have intense deserts, the Atacama Desert and other deserts over here on the west side. Okay, so tropical rainforest versus desert up in that area. Okay, you have the same thing here with the Himalayas. So the Himalayan chain, you have, notice all the green down here, you have the prevailing winds bringing water up that direction, or the clouds that direction. Rains all down here on this windward side in India, Nepal, Bangladesh, and then the Tibetan plateau is very, very dry. Okay, so desert formation as well as forest formation, those local climates being affected by mountain ranges. And sticking with mountain ranges, a thermal inversion. We talked about these already. A thermal inversion occurs where you typically have mountains, sometimes just hills, creating a valley. And it's a reversal of the normal air temperatures where you will typically have warm air down at the surface and then cooler and colder air as it goes up, and air and pollutants can just disperse into the atmosphere. A thermal inversion happens where you have this layer of cold air that gets trapped underneath a layer of warm air. Okay, the reason for that, typically, again, we're talking about valleys. So there's a mountain range, or at least, maybe a couple mountains and a couple mountains, and then a city down in the valley. So these buildings, those squares represent, or rectangles represent buildings. Sun rises in the morning. Okay, let's back up to the evening. During the evening, everything's cold. Okay, so you have cold air down here, and all of this is just going to be cold air, right? Because it's in the evening, and then the sun rises. Okay, sun rises over the surface of the earth, and it starts to warm this region. Okay, so you start to get some sun rays coming over. Those sun rays are going to go through there and warm this layer, but you still have that cold layer underneath. All of this air is still cold, and it creates kind of this boundary where they don't mix and they can't mix, and you're going to keep that cold air down here for much of the day. All right, that's going to trap all the pollutants in that air, so we'll do pollutants as purple. All of the pollutants are going to get trapped down here, and it's going to lead to what we typically would see is smog. Something like Denver's brown cloud is due to this. All right, so Denver is in fact in a valley. You have the Rockies over to the west, you have the Palmer Divide to the south, as well as some of the hills like Highlands Ranch. Highlands Ranch is called Highlands Ranch because it's a high land. Denver's down more in the valley. The only Aurora actually is above Denver. You can look down into Denver from Aurora. But then on the north side is the only, it's the exit for the South Platte, and it's not really not hilling Denver in. But Denver is more or less in a valley. So it gets these thermal inversions quite often where you see this layer very distinct of dirty air, which is the cold air, which is trapping all the pollutants. Okay, so that's what we're seeing right there down here in Denver. You see it also in Los Angeles a lot. Los Angeles is ringed by mountains and hills, and you're seeing it in Los Angeles too. So this is going to affect local climate as well because it's going to be relatively cool in these areas compared to surrounding areas, plus it's going to influence the pollution. All right, we talked about volcanoes and how they regulate climate already, so I'm going to go through this really quickly. But CO2 is a greenhouse gas. So in the long term, it's going to warm the climate. So that's the long term. Heavy volcanism is going to warm the climate because it's releasing lots of CO2. That CO2 is coming from the reaction of all of this heat and exposed to oxygen going through any rock that contains carbon. All right, there's a lot of carbon-rich rock out there. In fact, the Earth and rock itself is the largest carbon reserve on the planet. But I'm going to focus on sulfate aerosols. These are going to cool the planet, so they reflect sunlight back into space. Again, that's what albedo is, but we'll focus on that on another day. So they will reflect sunlight back into space, cooling the planet. Particulate matter will too as well. So that will lead to what we call volcanic winter if it is if it's intense enough. All right, we haven't seen a volcanic winter in the history of the human race, or at least civilization. But if Yellowstone were to erupt for whatever at whatever time it will, that would release so much ash and pumice into the atmosphere that it will lead to a volcanic winter. All right. Those both get globally distributed pretty quickly, especially if these sulfates are from a tropical volcano. For some reason, just due to the, not for some reason, but due to Hadley cells and due to the Coriolis effect, they just get globally distributed pretty quickly if it's from a tropical volcano. All right. The particulate matter and the sulfate aerosols are going to precipitate out pretty quickly, so they will lead to short-term cooling. So short-term cooling. When they precipitate out, that just means that they fall from the sky. All right. The CO2, though, is going to remain in the atmosphere for a very long time, so again, that is long-term. Okay. For a little bit more detail, I would encourage you to return to the plate tectonics lecture, where we talked about this in a lot more detail. All right, and again, same thing, we've already really talked about this. A couple of the examples. So in 1783, there was the eruption of the Laki fissure in Iceland, released so much sulfur aerosols that it cooled the planet very briefly, just for a couple of years. There was famine and plagues in everywhere from Japan and China to North America and Europe. Thousands in Europe died just from the inhalation of toxic gases. And then the famine that resulted from crop failure in Europe was one of the sparks for the French Revolution. All right, so these also, not only in terms of climatic impacts, have political and social impacts. In 1816, there was the year without a summer. That was from the Mount Tambora eruption in Indonesia. And what I wanted to show with this diagram is just temperature fluctuations due to volcanism. So we see that there is an overall trend of increasing temperature since the Industrial Revolution due to increasing carbon dioxide in the atmosphere due to human activity, burning fossil fuels. But within that trend, we see several years where we have low temperature years compared to the years before due to volcanism. So all of these eruptions leading to slightly cooler years due to the sulfate aerosols that are being emitted by those volcanoes. And obviously larger volcano eruptions, or eruptions that produce more sulfate aerosols, are going to have more of an effect rather than a smaller eruption. And then there is going to be mitigation of these effects or moderation of these effects based off of other conditions in the atmosphere, whether it's an El Nino year or a La Nina year or whatever. But going back to the CO2 though, when we're talking about the long term, that can have major impacts, and it can even lead to mass extinction events. So we haven't seen volcanic eruptions on this scale in our evolutionary or recent evolutionary history, right? The past really 60 million years. So the Cenozoic period, the past 60 million years. All right, they tend to have a global warming impact. So we see that right here at the border of the Permian and the Triassic, there was a spike of carbon dioxide and a spike of temperature, both of those increasing right there at the end of the Permian due to what they call flood basalt volcanic activity. It was the Siberian traps. What traps mean is like a giant area of flood basalt. Flood basalt is essentially like, think about Hawaii just gently flowing out lava. But think about that on a continent-wide scale. There's so much, this covers, huge regions, just large stretches of Siberia in lava that's half a mile or half a mile or a mile thick. So huge amounts of CO2 going into the atmosphere, leading to a mass extinction event. You also see a minor or a smaller little spike. I mean, actually, this one isn't even showing that spike, but there should be another spike right here at the end of the Triassic, because the Triassic-Jurassic was another period of intense volcanism as South America and Africa and North America and Europe rifted apart and ripped Pangea apart. But anyway, CO2 on the very long scale has a global warming impact. It has to be massive, massive volcanism, or at least a lot of little volcanoes all together in a very, short period of time. This is not what we're seeing today. What we're seeing today is from CO2 increasing from the burning of fossil fuels, and we'll talk about that on another day and the evidence for that. All right, so the learning objectives, just to return to those, again, input from energy by the sun. We didn't really talk about that a lot, but we did at least with ocean currents. Remember that all wind currents, all ocean currents are driven by solar input. Tectonic activity is the only thing that we'll talk about in this planet, except for, geothermal energy, volcanoes, all that is related to tectonic activity. Tectonic activity is the only thing that we'll talk about where the energy input is from the Earth itself, from the Earth's core and its mantle. Okay, but really the core. The learning objectives describe how the Earth's geography affects weather and climate. We talked about, sun's energy and geology, geographic factors, mountain ranges, and ocean temperatures, how all of those can affect climate. And we talked about rain shadows. Okay, and then we discussed thermal inversions and how they can moderate climate or affect climate in a specific area. We mentioned pollution, but we'll return to these when we talk about pollution. All right, don't worry about this enduring understanding, not for this unit. We'll talk about that, all those human activities much later on in the school year. Okay, what I really just wanted to talk about was how a thermal inversion happens, how that's related to the geography of the area, or how it's influenced by the geography of the area, and how it can trap pollutants, even if we don't need to know what those pollutants are right now. All right, so I hope you guys learned something, and I'll see you all in class.